So let's try some of these problems on inflation. Again, when we do these problems in this textbook, we're making some gross assumptions that our compound period is annual and that our interest rate is constant over the entire time. You're going to see that there's even some more ridiculous assumptions here, but let's read this problem. It says, suppose your annual salary today is $30,000. You want to know what equivalent salary will be in 20 years. That is, a salary that will have the same purchasing power. So assume 6% inflation. So it's not a bad question in the sense that if I make $30,000 a year now, 20 years from now, if I'm still making $30,000, I'm going to be very upset. The reason is $30,000 today is not the same as $30,000 20 years from now. So what would be the equivalent dollar value of $30,000 20 years from now? So here's where our assumptions start getting awful. Look at the assumption right here. It says assume that it's a 6% inflation rate. I already told you a realistic inflation rate is anywhere between 2 to 4% on average. So 6% is way above average. And not only are we assuming that it's 6%, which is one of the highest ever in history, we're assuming that it's going to be 6% every year for 20 years. So the answer we're going to get is going to be a bit ridiculous. But the idea of inflation is not. So how are we going to do a problem like this? Well, let's look at this. The first thing we want to realize is that our initial value here is $30,000. Our time here is 20. I told you we are always going to assume that it's annual compound interest rates. And then we have an inflation rate. Our R value here is 0.06. So let's go ahead and use our compound interest formula. A, we want to know what it is in the future, is P times 1 plus R over N raised to the NT, the compound interest formula where N is 1. So here we're going to have A equals P. Our initial amount was $30,000. We do 1 plus our R value was 0.06 divided by 1 because it's compounded annually. 1 times 20. Go ahead and plug that into your calculator now and see what you get. I'm getting a total value of $96,214.06. So if you had an interest rate or an inflation rate of 6% every single year, which is not possible, would not happen. But 20 years from now, your salary would have to be $96,000 to buy the same as a $30,000 salary today. So I just told you that's not realistic. What is realistic? My guess is probably about half that. You would probably want about somewhere between a $45,000 to $50,000 salary at least to have the same purchasing power. But again, you don't want the same purchasing power. I would hope if you worked in a field for 20 years that you'd be making a salary that has significantly more purchasing power. So let's go on and try example 10, see what it says. So suppose you purchase an insurance policy in 2015 that will provide you with $250,000 when you retire in 2050. So the $250,000 is not your present value, that's the amount in 2050. It says it's assuming an annual inflation rate of 8%. What a joke that is. There would never be 8% interest, and we're going to assume that it's 8% that entire time, but whatever, let's just do the problem. It says, what will be the purchasing power of the $250,000 in 2050? So $250,000 in 2050 is worth how much money today? Certainly it's going to be significantly less than $250,000. Okay, so this right here, that $250,000, that's actually my A amount. Now, I need to find my R, that's 0.08. Again, we are always going to assume in inflation problems that N equals 1 here. So the only thing left is to find time. So how are we going to find time? Well, we're going to do 2050, the year that it ends, minus 2015, the year that it started. That gives us a total of 35 years that this money, or that the value of today's money, is going to increase. 35 years of inflation. And so we are going to be using the formula now, P equals A over 1 plus R over N to the NT, because we want to solve for the present value. Let's plug those numbers in. So this would be P equals, well, A is the $250,000 that we want as a salary. We have 1 plus R, which is the ridiculous 8% that they're claiming, over 1 to the 1 times the number of years was for 35 years. Go ahead and plug this into your calculator and let's see what you get. I'm getting $16,908.64. So, right now you should pay approximately $17,000 for an insurance policy that would give you $250,000 when you retire. Again, this is quite ridiculous inflation rates. This isn't realistic, but it is giving you an idea of $250,000 today is not worth $250,000 in 2050, and vice versa. So there is something called the rule of 72. We're not going to use it, but how long does it take for the value of something to double? Well, usually it's 72 divided by the annual inflation rate. I do want to warn you here that the inflation rate here is a whole number, not the decimal. So if you were saying 6%, you would use the number 6. You would not use the number 0.06. So they're talking about here in their example, if you wanted to know if it was a 6% interest rate or not interest rate, inflation rate every year, how long would it take it to double? They do 72 divided by 6, and it's approximately 12 years is how long it would take to double. So again, here I would say 3 is a better number, even maybe 2 is a better number here. So how long would it take something to double value in the real world? You're looking in approximately anywhere between I don't know, I would say approximately 36 to, approximately 36 years. That would be dividing it by 2. I don't really want to go a higher inflation rate than 2 because over that much time, you're going to have a lot that are higher and lower. Okay. So what's the next topic about? The next topic about is the effective interest rate. So what is this about? What's an effective interest rate? And they give you kind of a decent example here. It says, what if one bank advertises a 7% annual interest rate compounded daily yields 7.25%? So what's the general question here? Here's the general question when it comes to these types of problems for effective interest rates. What if I told you that someone offered you a 7% interest or 7.1% interest on a loan? Which one of those two would you choose? Well, again, it depends on whether it's a loan or it's an investment. If it's a loan, you're going to want the smaller of the two because you want to pay them less interest. If it's an investment, you're going to want the higher of the two because it pays them a higher interest. Okay. As a separate problem, what if I said, what would you rather have? Let's presume this is an investment, so you want the higher one. So you would want 7.1% on this one. But what if I told you completely separately, you had two banks, one that wanted it compounded, I don't know, let's say semi-annually, and a second bank that was going to do compounded, let's say, I don't know, how about daily? Which one of those two things would you choose? Well, we learned from simple interest and compound interest that compounding more often is better if it's an investment. So if it's an investment, you would want the one that was compounded more frequently. If it's a loan, you want the one that's compounded less frequently. So now what happens is let's consider two different banks, Bank A and Bank B. Bank A is going to give you, and you're going to make an investment, Bank A is going to give you 7% interest. Bank B is going to give you 7.1% interest. If I was investing just on interest alone, I would choose the 7.1%, the higher interest rate. But imagine if Bank A said it was compounded daily, and Bank B said that it's compounded semi-annually. What do you choose now? Because if I went off the compound period, I would pick Bank A because it compounds more frequently. So which one means more, the interest rate or the compound period, or is it a combination of the two? Which one of those two banks should I pick? And that's where you're going to use the effective interest rate. What the effective interest rate says, essentially, if you invest $1 at the end of the year, how much did you get? How much interest did you get? It is an effective rate, so it is a percentage, so we're going to want, if it's an investment, the higher of the two percentages. This is where we're going to get the formula and complete the problems on the next page. But this is the general idea. Which one of these two banks do I invest in? Bank A with a lower interest rate but better compounding period, or Bank B with a higher interest rate but a lower compounding period? We're going to figure out how to compare those two using the effective interest rate formula.